Yes, we are continuing our discussion about closed form solutions. And we obtained solutions for simply supported columns. And our function that we postulated was this: a psi of x equals x in fourth power minus 2x cubed L plus xL cubed. Now, we would like to discuss a case when column is clamped at both ends. And on this case, we also start with the following polynomial: a0 plus a1x plus a2x squared plus a3x cubed plus a4x in fourth power. So boundary conditions are psi at 0 equals 0. This gives me a0 equals 0. Then psi prime at 0 equals 0. That gives us, of course, a1 must be 0. So this is 0 and this is 0. Then we have left, we are left with psi of x equals a2x squared plus a3x cubed plus a4x in fourth power. Now psi at L equals 0, which gives me a2L squared plus a3L cubed equals minus a4L in fourth power. And psi prime of L equals 0. And we get 2 times a2L plus 3 times a3L squared equals minus 4 times a4L cubed. No, I'm talking clamped at both ends. Clamped. Now, if this is the case, then we can find, we put a4 equals 1. And we have a2L squared plus a3L cubed equals minus L in fourth power. 2a2L plus 3a3L squared equals minus 4L cubed. So from here we can say eliminate a3, etc., and we get the following final expression: psi of x equals psi of x equals x in fourth power minus 2 times x cubed L plus x squared L squared. So this is an expression for clamped, and indeed function is 0 at 0, first derivative is 0, function at L will be L in fourth plus L in fourth minus 2L in fourth, and first derivative will be 4x cubed minus 6x squared L plus 2xL squared. So at L will be 4 plus 2 minus 6, which is 0. So for clamped, we have to postulate these conditions. Now, if this is the case, then the differential equation itself is d2 dx square d of x d2 psi dx square plus p d2 psi dx square equals 0. So if that is the case, we can say that d again equals b0 plus b1x plus b2x square. Is it right? That is a second order. This will be second order. So it will be fourth order. Second derivative will be second order. And here we have second order. So everything is okay. So we have psi prime equals 4x cubed minus 6x square L plus 2xL square. Psi double prime equals 12x square minus 12xL plus 2L square. Now this should be multiplied by d of x. That means b0 plus b1x plus b2x square times 12x square minus 12xL plus 2L square. Okay, so we get, first of all, free term, b0 times this one. So 2L square b0. Okay, there is no other terms. Plus x will be. Now b0 times this will give x minus 12 L b0. Okay, b0 times this term. Now b1 times this term also gives us. Then it will be plus 2L square b1. That gives us terms with x. Now plus x square. This term times this term will give minus 12 L b1. This times this. Now will be this times, now this times this also. It will be minus 12 b0. And then this with this, plus 2L square b2. That is x square, plus x cube. X cube will be x times x square. So 12 b1. And this times this, minus 12L b2. And then x in fourth power will be 12 b2 x in fourth power. Now that is a second derivative. Now I have to calculate. Now this is actually this. Let us write it down. This is what? D psi double prime. Now we can calculate d psi double prime prime. Okay, because I have to calculate two derivatives. Will be this will disappear. So there will be some term, free term. That is this one. Plus 2x minus 12L b1 minus 12 b0 plus 2L square b2 plus 3x square 12b1 minus 12lb2. And will be plus 48b2x cubed. Now when I differentiate once more, d psi double prime equals, this term disappears. So it will be 2 times minus 12 lb1 minus 12 B0 plus 2L square B2 plus 6x 12B1 minus 12LB2, and then will be plus 3 times this term. I hope that you are paying an attention and you are checking after me. Okay? So this will be 144 B2x squared. Now, we also have this second derivative. So let us write down p times second derivative equals 12x squared minus 12xl plus 2l squared times p. Now we have to add them. Deep side double derivative. Okay, so we have, so when we add, we can immediately also demand what should be 0. 2 times minus 12 LB1 minus 12 B0 plus 2L square B2, that is this term, plus this term. 2L square P must be 0. Okay, plus this term, free term. Now with x, 6 times 12B1 minus 12LB2. Now this term, minus 12LP must be 0. Yeah, I took this term and that term. Now we have this term. 144 B2x squared, and then plus 12 P equals 0. How many unknowns do we have? We have B0, B1, B2, and P. 4 unknowns. How many equations? 3. Okay, so we have 3 equations for 4 unknowns. So that means that then there will be infinite amount of solutions. So how much is P? So imagine that B2 is a coefficient. Free coefficient, so to say. Then P equals minus 12 B2. Oh, somehow I wrote here 144. This should be taken away, this x squared, because so that is P equals minus 12 B2. So that means that B2 must be negative. Or we can write down that P equals 12 absolute value of B2. Now we go back. So we substitute this here, and we get, so 6 we can, okay, there is 6, 12B1 minus 12LB2 minus 12LP equals 0. Okay, first of all, by 12 we can just get rid of 12. We have 6B1 minus 6B2 L minus LP. Minus LP means that P equals minus 12. So that will be plus 12 B2L equals 0. Yes? Because I just substituted this minus 12 B2 here. So minus get plus. Are you with me? So from here we get 6b1 plus 6b2l equals 0. So that means that b1 equals minus b2l. That is b1. Now we have this first equation. Pay attention to this one. We have 2 times minus 12lb1 minus 12b0 plus 2l square b2 plus 2l square p equals 0. Now we substitute here. 2, okay, we have minus 12lb1, but there is minus here, so will be 12l square b2. Yeah, I substitute this here. There will be minus 12b0, then plus 2lb2. And then there is this minus 12, p equals minus 12, minus 24 L square b2 equals 0. How much is p? b2, so there is no L square. Oh, no, there is L square. But what happened here then?
You need L square.
Oh, here I need square? Okay. So this 2, okay, 2 and 24, we get 12 here. So then I will get 12 plus 2 will be 14 L square b2 minus 12 b0. Then we have minus 12 b2L square equals 0. So 14 minus 12 is 2. 2 b2L square minus 12b0 equals 0. So b0 equals then 2 12ths or 1/6 b2L square. So what we got? P equals minus 12b2. It is one result. Second is d of x equals b0 plus b1x plus b2x squared. This equals b0 equals b2l squared over 6 plus b1. b1 is minus b2l and then x. And then there is plus b2x squared. Or that could be written as follows. b2 x squared, okay, let us start with this. And then it is L squared over x, 6 minus Lx plus x squared. Let me check. Yes. Okay, so let us check this function. So that is d of x. Let us just calculate first derivative of x. Will be b2, this is 0, minus x plus 2x. Now where is it 0? When x minus L. When x equals L over 2. So that is a symmetric function. So d of x. When d equals 0, so d of x divided by b2 I can calculate. Divided by b2l squared. So when x equals 0, then it is 1/6. Now when x equals L will be Okay, let us calculate here. How much is here? L square minus L square, okay, when x equals L. So it's the same number. Now let us calculate in the middle. So that is L square over 6 minus L times L over 2 plus L over 2 square. So that will be L square 1 6 minus 1 4 plus 1 4. What is this? Minus 1/2, sorry. Minus 1/2. That is L square. So then it will be L square, and then this is, say, 12. We will get 2 minus 6 plus 3. 3 plus 1 is 5. 5 minus 6 minus, what is minus? Yeah, that is actually, then it is what? Minus 3, 1/12, yes? Yeah, that is minus L square divided by 12. Say it again.
So it's negative.
No, negative is okay, negative, because d of x,
It's multiplied by b2, it is negative, so it's
say it again.
no, okay, I understand.
No, b2 is negative, but if b2 is negative, I don't understand here what we got. Yeah, we should get, here we should have, I mean, look please, here we should have absolute sign. That is what we got, or we got with sign minus? I don't know, I got with minus sign. Minus everywhere. Here is minus.
No, but instead of p minus 12b2,
Say it again.
you substituted p equals minus 12b2.
Yes. I don't know. I got here, okay, let me write down. 6. Probably I made somewhere mistake. Everything is correct except the sign. I got in my paper d of x equals minus b2 L square over 6 minus Lx plus x square. Is it possible? I got with minus sign. So please check. Now, if this is the case, then when x equals 0, we get d over b2 L square equals 1/6 with mine, okay, b2, absolute value of b2. Okay, this equals b2 absolute value L square over 6 minus Lx plus x square. if that is at 0, at x equals 0. Now, x equals L, we get L squared over 6 minus Lx plus L plus L squared. So that is L squared over 6. Now what happens when x equals L over 2? L squared over 6 minus L over 2 plus L over 2 squared. Then it is L squared 12. 12 divided by 6 is 2. Minus 12 divided by 2 is minus 6. 12 divided by 4 is 3. So something does not make sense here, something. Please check. Okay? As a homework. It is better to do by hand. Of course, please also use the pen and paper, not just a hand. Any questions? Please do this by tomorrow and communicate this to me because I'm very much interested what is happening here. You can do it together, etc. Now, page 7. Vibration and stability. So imagine that we have this our simply supported column. The length is L. And it vibrates. If it vibrates, then differential equation will be what? So imagine EI is constant. Then will be EI d4w dx in force power plus P d2w dx squared minus plus rho A d2w dt squared equals 0. So these derivatives are partial. And in the beginning I thought I will do something else. So W equals small w of xt equals a capital Y of x times sine omega t. Omega is a frequency. So we substitute, we get EI d4 capital Y dx in force power plus P d2 capital Y dx square minus rho A omega square Y equals 0. Now we get as follows. Now we get the following. Y, because it is simply supported, then Y at 0 equals Y second derivative at 0 equals 0. Y at L equals Y second derivative at L equals 0. So we can say that Y of x is a function that is, say, some constant times sine n pi x over L. because it is a simply supported column, and this function satisfies all the boundary conditions. Now we substitute this a times sine n pi x into this differential equation, and we get EI, this is a, force derivative will be n pi over L in force power minus p n pi over L squared. Then minus rho a omega squared sine n pi x over L equals . Now, if this is 0, a can be 0. A is 0. If a is 0, then y of x equals 0. But this contradicts to experiment, because we see that beam is vibrating, or column is vibrating. So a is not 0. Now, sine n pi x over L equals 0 when x is 0, x is L, and also depends on the, when x equals L over n pi, L over n, sorry. For example, if n equals 2, it equals 0 when L equals half L. That means that not always sine n pi x over L equals 0. Not always. For some points only it equals 0. But we have entire expression is 0. Entire expression is 0. So that means that only this one should be demanded as equals 0. Nine. So what is left then is as follows: EI n pi over L in force power minus p n pi over L square minus rho a omega square must be 0. So from here we get natural frequency. Omega square equals EI over rho a n pi over L in force power minus p over rho a n pi over L squared. Now we can actually say that this is omega square as a function of p, because p is here. So then we can call EI rho a n pi over L in force power minus p rho a n pi over L squared. Now what happens, how much is omega square at 0? That means that this is omega square p when p is 0. It means that the beam is just vibrating freely without any load. No axial compression. So this is very simple, just put this 0. So we get omega squared at 0 equals EI rho A NP over L in force power. So we can actually write it down that omega square P, that is actually nth frequency, equals omega square nth frequency 0 minus P, that is P, rho A n pi L squared. Now what that means? What does it say? Conclusion. Natural frequency decreases with the increase of axial compression. Now, how does it decrease? Linearly. Because P is here as P in first power, not P square or something. So that means that we get the following. The figure is like this. Omega square NP. Now at 0, that is P. That is omega square N0. And then there is some linear relationship, something like this. Okay? Because it says minus, because it decreases. Now we can say, question. Now, what value is obtained by frequency when P goes to P critical, and that is pi square EI over L square? What happens when P comes to the Euler load? It's very simple, just let us substitute. We have omega n square P. So what value is obtained by frequency? Let us calculate omega 1 square P. That equals first, so we have this one. Yeah, this n we put 1. EI over rho A pi over L in force power minus P. P is pi square EI over L square, and times pi over L square and 1 over rho A. I just substituted. So we get EI over rho A pi over L in force power minus EI, look, here is EI and there is rho A. EI over rho A. So pi over L squared, but then we have squared. So that is 4. So this expression and this expression are equal. So that is 0. What does that mean? This means as follows. How much is a period of vibration? Period of vibration is 2 pi divided by omega 1. So that will be 2 pi divided by omega 1. We have omega 1 squared, so we have EI over rho A pi over L in 4th power minus P, and then pi over L squared, and then there is 1 over rho A. So that is a period. Now what is a period? Period is something like this. That is a period, time, in which pattern is repeating itself. Minimum amount of time in which pattern repeats itself. So that is this P. That is this T. Now, what happens when P increases? What happens with the period? If frequency decreases, then naturally period is increasing. Now, when P goes to P critical, P Euler, then T becomes what? Infinity. That means that after how much time structure returns to the same pattern? Does the pattern return? After how much time? Infinite amount of time. Or never. Is it right? Because if it takes infinite amount of time to come back, that means that Woody Allen in one of his movies could have said, instead of that he's leaving, he would have said that he's coming in infinite time or something like that. So, period goes to infinity, or frequency goes to 0. So, frequency going to 0 at the critical load, the natural frequency vanishes. Any questions? Okay? Frequency vanishes. Now, interestingly, I just had this thought now, just actually 1 second ago. So, if we consider simply supported column, and it has what? Remember, we have this d2 dx squared d of x, d2w dx squared, plus p w second derivative, then minus rho a omega square w is equals 0. So for that column which EI is changing. If you remember, when d of x equals what? How much was d of x? D of x was, I think, b2 x squared minus XL minus L square. Yes, that is what we had before for simply supported column. W was, do you remember what was W? W was x in fourth power minus 2x cube L plus XL cube. The question is question. What should rho be so that, I mean, we have solution for vibrationals. Is it right? We have to calculate what expression is coming here. Is it right? But this expression, no, I don't think that it will work. Because, look please, if this is fourth order polynomial, then this is a second order polynomial. If it is a second order polynomial, then this is a fourth order polynomial. So in order to have the somehow second order polynomials, then rho should be fourth order divided by, rho should be 1 divided by the second order polynomial of sorts. So what I'm saying is that solution of this kind is we are unable to extend for vibration case. Polynomial solution does not exist. Because this will be the second order polynomial, yes, for that D. If it is a second order polynomial, we cannot possibly get here. W is a fourth order polynomial. So naturally, fourth order polynomial and second order polynomial cannot match each other. Okay? So there is no possibility to match. Now let us just check what happens in the case of Duncan problem. Duncan took fifth order polynomial. So if he took fifth order polynomial, once you differentiate 2 times, you get third order polynomial, but this is 5, so it cannot work either. So for vibration case, this type of solution does not work. You see, that means that this type of solutions are very specific. You may want to write. Polynomial solutions are very specific. They are lacking generality. Okay? Now I would like to assign some specific homeworks. 13. So, and let me write down 1. Homework, no, not 1, but A. And I will write here several homeworks. So we have d2 dx squared d of x, d2w dx squared plus d dx n of x dw dx. Now we have, let n of x equals p, small p, L minus x. So that means that that is a column like this. P. And if I will cut here, say x, then n of x here will be this value, yes? So small p times this distance. That is L minus x. Okay? Now boundary conditions are, we know what it is here. W equals 0, W prime equals 0. Here, W second derivative equals 0. But also W third derivative equals 0. Why? Because there is no concentrated load. This is a distributed load. Okay? So W equals A0 plus A1x plus A2x squared plus A3x cubed plus A4x4. Find psi. Oh, that is psi, sorry. Not W, but psi. Then which order should d of x be? Find p critical and d of x. So that is problem A. Now problem B. Did you write? Problem B. So again, the same equation, d2 dx squared, d of x, d2w dx squared, plus d dx, n of x, dw dx equals 0. Now n of x equals p, L squared minus x squared divided by 2L. Simply supported on both sides. Find, yeah, in that case also, please graph, plot d of x in previous, in A. Plot d of x. Now find p critical, d of x, plot it. Now problem C. The same problem, but clamped free. Yeah, problem D. Problem A, but simply supported. Okay, please do this by Maple or Mathematica. So I think that I will assign you these 4 problems. That is very simple problems. Plot here, plot d of x everywhere. Plot d of x, just 4 problems. Any questions? If there are no questions, yeah, just let us discuss one thing actually. Discussion of homework. So I will just write it down. d2 dx square d of x w second derivative plus d dx. Okay, say PL minus x w first derivative. This equals 0. Now, w is fourth order polynomial. Now, if w is fourth order polynomial, then this guy is a third order. Yes, because this is the first derivative. Now, this guy is which order? This red guy. This w prime is w is fourth order, first derivative is a third order. How much is this product? What order of polynomial, Mr. Penteras? Fourth order. Because third order I multiplied by function. Now, what order is this one? This green thing. You don't see whether, do you see that it's green? Okay, not very much. Okay, what order is this? Third order. Because we differentiate it. Now, we want this to be also third order. Is it right? Because if this is third order, then this also should be the third order. Now, this is w is fourth order. This w double prime is second order. Now, this is, say, order alpha. So this thing in expressions is alpha plus second order. And this is minus 2, because when I differentiate, the order goes down every time. So this is alpha. So alpha should be 3. So d of x is a third order polynomial. Okay, in the previous case, d of x was a quadratic function. Now d of x is a cubic function. Now one more thing, another discussion. d2 dx square d of x w second derivative plus d dx, and that is, what did we have here? P L square minus x square 2L, and then there is w prime equals 0. Now, that is this, that was problem B, I don't remember which problem. Now, again we start. That is a third order polynomial. So what will be now D? What order will be D now? Can you guess immediately without calculations? Again, what we had is as follows. Look, please. When n of x is 1, so to say, yes, this function is 1, then we had p times second. So then d of x order was 2. When this is pl minus x, the order is 3. And if here that is pl square minus x square over 2l will be what? 4. Why 4? It's very easy to calculate. And this is a third order polynomial. Then this guy is a fifth order polynomial. So then this is fourth order. So because there is w is fourth order and there are two derivatives here, then in order this to be fourth order, this should be the fourth order. Now, can we do vibration case here in this case? In this case, we can do vibration. Why? Because this is a fourth order polynomial, is it right? So if I will add minus rho a omega square w equals 0, this w is a fourth order polynomial. So then everything will work again. Because this is a fourth order, this is fourth order, and this is a fourth order. You got it? So in this case of n of x, additional homework will be do the vibration case. Also. Okay? Any questions here? Naturally, you know that I'm not checking whether you do it separately or you do it with someone else. I'm not opposing that you combine your efforts and you do it with someone else, but then responsibility is of each of you. And when you submit the homework, you can write that this homework is by person C and person D. And then you write your names. So I don't mind. I'm not against. That just means that you combined your efforts. Because you can do it anyways without me authorizing it. So, therefore, I'm authorizing it. So it is actually good to have some teamwork. Any questions? Any discussions? Were you able to obtain some solutions that are like solutions by Mr. Duncan, but different from his? Mr. Penteras, were you able to obtain some solution like Duncan? Yeah, past homework. Homework for today. You obtained some new solution? Different from Duncan? Okay, I will check, because if that is the case, then I will ask you next time. Please come to me before the lecture, say half an hour before the lecture. If it is correct, then we will put you here and you will tell us. It's because Ms. Gentilini said that she was unable to obtain. I think there is no another solution. Yes, that is what you said. What about Mr. Gomez? Did you obtain any new solution? Okay. Okay. Maybe you can get Ms. Gentilini and Mr. Gomez, maybe you can get with Mr. Penteras and get a consultation. Either he will find mistakes in your work, you did not have maybe enough time to make a mistake, or you will find mistake in his work. I mean in Mr. Penteras' work. Now we will discuss the following topic. I think we would like to come back to chapter 2. If you remember, we are going with columns and then come back to Lyapunov. Is it right? We are, so to say, dancing on two weddings, not just one wedding as someone recently attended. So we go into two ones. One is column wedding and the other is Lyapunov. So let us consider a system. You have these pages. So we consider this linear system. dxj dt equals k from 1 to n, ajk xk. This is, of course, an abbreviation. This writing is an abbreviation. Say if j equals 1, then we have dx1 dt equals k from 1 to n, a1k xk. And that equals a11x1 plus a12 x2 plus a1n xn, etc. So we write it dxj dt equals k from 1 to n, ajk xk. So this is a summation, and j itself takes values 1, 2, 3, etc., n. Naturally, ajk forms a matrix because that is n by n. So this is a matrix A. So ajk's are given. So this equation actually can be written like this, like x dot equals ax. So that is a very short and very neat notation. X dot equals ax, where x dot, x is actually a column, and that is the derivative of the column. Derivative of the column is actually column of derivatives. dx1 dt, dx2 dt, etc., dxn dt. Now this is A, that is this matrix A, as we said, and that is X. And that is how we are multiplying actually matrix in order to obtain the J's, in order to obtain J's row, we just fix J, A, J, K, X, K. That means that I multiply the elements of J's row by the elements of column XK's column, XK. Now what Lyapunov suggests is as follows. To form the following function, and that is what? Some b. Let us take some function, some b. bx, and x from the right is bx, and then it is multiplied by x transpose. We will continue it next time. I'm getting the signal that lecture is over. Thank you.